Video will walk you through how to estimate nonlinear regression, model nonlinear relationships using regression. And I apologize, I've got a little bit of a cold, so um, audio may be worse than normal. So the example that we're going to look at, this is real data. These are actually my electricity bills and average temperatures from 2015 October through 2020 December. So these are actual electricity bills from my first home. And we're going to look at how we can capture some nonlinearity in the relationship between two variables using the polynomial and then the natural log. So the first thing I want to do here is plot this data. So I'm going to go ahead and create a scatter plot. And what we can see is there's a clearly a very clear nonlinear relationship between the temperature outside, the average monthly temperature, and my electricity bill. It's not that perfect U shape or upside down U shape like you would get with a second degree polynomial, but we can clearly see that if we increase the temperature when the temperature is low, not much is happening, but once it goes above 70 degrees and it gets warmer, my electricity bill tends to increase pretty quickly. And more than likely what's going on here is once the average temperature outside exceeds 70 degrees, that's when I start running the air conditioner. And as I run the air conditioner more and more, we use more and more electricity. So the hotter it gets, conditional on being above 70, we tend to see a pretty significant increase in the electricity bill, but below 70, we don't see much. And what's going on down here, I had gas heat, so I did not use electric to heat my house. I used gas to heat my house. So that's why my electric bill is not changing that much as we at the lower temperatures. So if I had electric heat and used electric to run the AC, we might expect to see higher electric bills when the temperature is really low, signaling the increase in heat usage, and then higher when the temperature is high, indicating more AC usage. And in that middle range, we might see something where I'm not running the heat or the AC. So in practice, you don't see these perfect nonlinear relationships the way we saw in the notes with that very exaggerated polynomial and log models. But this is what we typically see. One interesting thing about this using a scatter plot is you can actually fit a polynomial model and a natural log model, natural log of the dependent variable, using the trend line. So if you already have the plot up, you can go to chart line, add chart element, trend line. We want more trend line options right here. And that's what we get if it's linear. And we can see a straight line does not model this relationship very well. If we click on exponential, we can see it does a little bit better capturing that nonlinearity. Again, not perfect, but this is just for a demonstration. And if we go to polynomial order 2, notice that does a pretty good job capturing that nonlinear relationship. So you can just filter through these exponential. This is the same as a natural log of the dependent variable. This is the linear that we've always done. This polynomial is going to include temperature and temperature squared into the model. So if you only have one independent variable, you can model the relationship this way. If you have more than one independent variable, that's not going to work. So let me show you how to do this using regression so that you always have a method that works even if you have more than one independent variable. So if we want to estimate the model where we have temperature and temperature squared, what we have to do, and again, we're just going to ignore these other terms for now. We're not going to worry about the month and the seasons, is I want to insert a column right here and create another column called average temp squared. And because if we want a second degree polynomial, we have to include temperature and temperature squared in the regression. So this column right here is just going to be equal to the average temperature variable squared. So what you're going to see in column E is just the value in column D squared. And now when we estimate the regression, now I always click the wrong one first. We go to regression. Again, ignore everything that's in here. It's just left over from some previous example. So delete anything that's already there. Our Y range is going to be the electricity bill. So again, I'm highlighting that first cell, doing Control Shift down. My X range is going to be temperature and temperature squared. So I want columns D and E. I'm going to do Command Shift down, and that will give me D1 through E64. That's going to include those two variables. Always check labels, output range. Let's just put this somewhere that we're not going to overwrite anything, and hit OK. So here is the regression output. I'm going to go ahead and just to make life a little bit easier, I'm going to remove some of these decimal places. Okay. So we can see the R square is 0.64. So the variables temperature and temperature squared explain 64% of the variation in the electricity bill, which is more than half, which is not surprising because if your electricity bill is primarily being driven by the temperature or the how much AC you're using, that makes sense. It's going to explain quite a bit. We also have other things like how much lighting we use and how many people were in the house over that time frame. My daughter was born, had family visiting. So that explains some of that other variation in the electricity bill. But just the variables temperature and temperature squared explain 64% of the variation in the electricity bill. So that's one way of modeling that relationship. So notice we get an intercept and then we get two coefficients on temperature. And remember that we don't have a single slope term anymore. So the slope or the effect of temperature on the electricity bill now depends on the electricity bill. So if we go back here and look at, just add this plot back here, we can see, I'm going to go ahead and fit that polynomial back to it as well. And it would be the exact same result. I'm just, I'll put the equation on there just so we can see that it is the same. So polynomial order 2, display equation on chart, display R squared. So we can see here we get the exact same answer. Again, rounded. Again, I apologize. Excel puts this in the most inconvenient place possible. Let me increase the font size there. So we can see we get the exact same result. The intercept is 196.58, same intercept we got here. The coefficient on temperature, which is just generic X here, is negative 6.57. And the coefficient on temperature squared, rounded to 2 decimal places, is 0.07. But we can see if we look at this line, the slope depends on the value of temperature. So if we're over here, the slope would actually be negative. Over here, the slope would be positive, and somewhere in the middle, the slope would actually be 0. So we can actually determine exactly what that slope is going to be. So I'm going to just come below this and put temperature and then slope. So let's set the temperature to 40 degrees. The slope is always the coefficient on the linear term plus 2 times the coefficient on the squared term multiplied by the independent variable. So this is going to be equal to the coefficient on temperature plus 2 times the coefficient on temperature squared. And we're going to multiply that by the value of temperature. And notice we get a negative number. And if we look over here at 40, the slope of this estimated line is negative. So this tells us if it's 40 degrees outside and the temperature increases by 1 degree, we expect the utility bill to decrease by $1.32. So the temperature, the electricity bill actually goes down when temperature increases when it's 40 degrees. Now if we put 70 degrees, we get a positive coefficient. And if you look over here at 70, the slope of that estimated regression line is positive. So this tells us when it's 70 degrees outside, if it increases, if the average temperature for the month increases by 1 degree, we'd expect the utility bill to increase by $2.61. So this is how we determine the slope or the effect of the independent variable on the dependent variable when we model something using a polynomial. So the next thing we want to do is estimate a regression where the dependent variable is the natural log of electricity. So I'm going to come over here to the right. I'm going to insert some space right here. Let's call this LN bill. And this is going to be my new dependent variable. So my dependent variable is going to be the natural log of the electricity bill, and my independent variable will just be average temperature. So to get this column, we just take the natural log of the electricity bill, and we run this down. And where you have to be careful is I'm not sure what happened there. You have to be careful here because you cannot use the natural log of a dependent variable if your dependent variable takes on negative values, because the natural log of a negative value is undefined. But here all of our bills are positive, so everything is going to work out okay. So I'm going to go back to my regression tool here. And my y range is now going to be the natural log of the dependent variable. So I'm going to click that, Control Shift down. So G1 to G64. And my x range is just going to be temperature. Now you could add the temperature squared. That model is perfectly valid. But for the ease of interpretation, we're just going to use one independent variable here. From the output range, I want to put this down here so I'm not overwriting anything. And hit OK. So now we have our output when the dependent variable is the natural log of the electricity bill and the independent variable is the average temperature. The R square is 0.32. Now you have to be careful because you cannot compare the R square from the polynomial regression to the R square for the natural log regression. The R square measures the amount of the variation in the dependent variable explained by the independent variables. If your dependent variable changes, the total amount of variation to be explained changes, and you can no longer compare the results. So we cannot compare this R square of 0.32 to the R square of 0.64 and say one's better than the other. So if we look at this, again, let me just go back up here to the scatter plot. I want to take this off. I'll go back to my trend line here. Let's do exponential. Again, always puts it in the worst possible spot. I'm not sure what it is doing here. Okay, so ignore that R square value. I'm not sure what's going on with that R square value there. But what I do want to show you is the coefficient on that. The coefficient's the same. So notice this gives it to you in this format where it's not the natural log of the dependent variable, it's actually temperature, and it has this exponential model on the right hand side. This coefficient 0.0214 is exactly what we get right here. So this model is the same. Again, ignore that polynomial model. I'm not sure why that's still on there. So this coefficient right here, 0.021, is the exact same coefficient that we get right here. So if you only have one independent variable, you can model that log dependent variable relationship using the exponential trend line, and you'll get the exact same results. So what we would say here is, remember, when the natural log of the dependent variable is used, we have to multiply this coefficient by 100, and that will give us the percent change of the dependent variable. So if we round this to 2 decimal places, I'm just going to go ahead and format this as a number here, 2%. So this says for every 1 degree increase in average temperature, the electricity bill increases by 2%. But notice that always assumes an increasing relationship. It always assumes that if it gets warmer, the electricity bill goes up, and that may not be perfectly consistent with the data that we're observing, because we do see a slight decrease here, and then an increase over here when it's above 70 degrees. But this natural log of the dependent variable produces a coefficient that we multiply by 100, and it's now the percent change in the dependent variable for a 1 unit increase in the independent variable. So this tells us, using this polynomial model, the slope is negative. It bottoms. The relationship is negative. We find a minimum, then an increase. With the log of the dependent variable, we're actually seeing that it's always increasing, and it increases by about 2% for every 1 degree increase in the average temperature. And just for fun, let me just go ahead and add the linear model to this so we can make a comparison. So let me go back here to data analysis. So I'm going to use just the electricity bill as the dependent variable. My independent variable is going to be the same, average temperature. Let's put this where we're not going to overwrite anything. And this says Again, we get an r-square of 0.46. So we can compare the r-square from the polynomial model of 0.64 to the r-square of the linear model, and we can clearly see that the polynomial model explains more of the variation. So it's doing a better job than the linear model. And the linear model says for every 1 degree increase in average temperature, the electricity bill increases by $1.21. So those are the three models that we talked about. In this case, the polynomial is clearly the best. It is the best fit just visually. We can see that it's fitting the data better than the log or linear model. But just be careful when you're estimating these models. Make sure you understand the units. Make sure you understand how to interpret the coefficients. That you're careful to multiply that coefficient by 100 when you have the natural log of the dependent variable. And for that polynomial model, you have to combine this information to estimate the slope. The slope is always the coefficient on the linear plus 2 times the coefficient on the square term multiplied by the value of the independent variable. So the correct model depends on your situation. I highly recommend plotting the data, doing some just visual checks to make sure everything looks okay before you start estimating these regressions.